Good morning, ladies and gentlemen. My name is Ricardo Batista, and I will present you the paper entitled Fatigue Crack Propagation Direction under Different Loading Conditions using MTS and MSS criteria. I will start with an introduction to the problem and, of course, describing the fatigue crack propagation and crack propagation direction criteria. We will then talk about the fatigue crack propagation algorithm used, the specimens geometry used on our numerical simulations, and of course we will see the results and end with the conclusions. As we know, a fatigue life can be divided into three stages. The first is the fatigue crack initiation, then crack propagation, and if the crack is not stopped, the failure. Now, fatigue failures happen due to poor component design, maintenance, components or set of components assembly problems, and external influence such as environmental effects. Now, this is true on many areas of the industry, but the railway tracks and railway industry is one area where fatigue crack propagation can lead to catastrophic events. In the case of fatigue crack propagation, what we need to know is the crack length along a given number of cycles. And taking this crack propagation curve, we can of course derive the Paris law or any material behavior equivalent equation that allows for the control and fatigue life prediction of the crack. Of course, fatigue crack propagation does not always happen on a straight line, so we have other conditions beside pure mode 1 opening conditions. When we have mode 2 and mode 3 shear modes, then we can have the crack propagating along a different direction due to mixed mode conditions. This can happen due to specimen or component geometry, so we can have mixed mode conditions due to component design, like when we add a welding detail to the specimen, or we can have different crack opening modes due to the loading types. So if we have a railway track, for instance, for higher loads, we can have pure mode 1 loading conditions. But when we add different types of loadings, like the rolling of the wheel on top of the railway track, now this can also lead to pure mode 2 crack opening conditions. When mixed mode or pure mode 2 conditions are established, then we need a criteria to determine crack propagation direction. We can use criteria based on the stress intensity factor, and these criteria take into account the stress field and the direction where mode 1 or mode 2 is maximized. The maximum tangential stress criteria considers that the crack will propagate along the direction where mode 1 is maximized. This can be very useful for proportional and mode 1 and mixed mode loading conditions. But for non-proportional or mode 2 dominated propagating conditions, then the maximum shear stress criteria that considers propagation along the direction where mode 2 is maximized, the criteria should be used. In order to simulate the fatigue crack propagation problem, we need an algorithm that updates the numerical model with a crack that is growing from increment to increment. Our algorithm uses MATLAB to update the model and to determine the new crack length and propagating direction. It uses Python to generate the model and Abacus to to solve the finite element problem and calculate the fracture mechanic stress intensity parameters that are used to determine the new crack length and the new crack direction. On our simulations, we have used two types of specimens that allow for proportional loading, the CTS specimen and the 4-point bending specimen. The CTS specimen allows for pure mode 1 to pure mode 2 loading conditions by varying the position of the applied load, while the 4-point bending specimen allows also from pure mode 2 to almost pure mode 1 conditions by varying the position of one of the loading supports. Of course, if we want to analyze non-proportional conditions or real-world loading conditions, then we can simulate a railway track supported by sleepers. In this case, we have simulated the longitudinal loading of the track created by different environmental temperature conditions and a transversal loading that moves along the rolling direction and simulates the passage of the railway wheel on top of the track. Starting with the results for the CTS specimen, we can see 4 different conditions. The first 2 are dominated by mode 1 conditions, and the crack propagation was simulated using the MTS criteria. When the crack propagates horizontally due to pure mode 1 conditions, or is slightly deflected by mixed mode conditions introduced by an incline load. As the load or the specimen continues to rotate, we introduce higher mode 2 conditions, and many authors consider that for load angle superior to 75 degrees, then the MSS criteria should be used to predict crack propagation. And on the last case, where we have pure mode 2, then the crack also propagates horizontally, but now due to pure mode 2 conditions. The same conclusions can be derived from the analysis of the 4-point bending specimen, where we cannot achieve pure mode 1 conditions. So even when the support is placed on top of the crack, we can still see some crack deflection. The deflection increases as the loading support is moved to the right. And when pure mode 2 conditions are established, then we can see that the MSS criteria predicts the crack to propagate vertically, but the MTS criteria would predict a deflection of the crack along the direction that maximizes mode 1 and not mode 2. So finally, when we consider the whole track and a load that moves along the direction of the rolling wheel, then we can see that the mode 2 is dominant for a crack starting from the base of a welt. In this case, the crack will propagate along an horizontal direction according to the MSS or mode 2 criteria. Eventually, the crack can actually bifurcate and start to propagate along a direction where mode 2 is dominant. This bifurcation can happen because both on the positive and the negative side we have similar values for the maximum MTS or mode 1 criteria. Therefore, we can conclude that fatigue crack propagation simulations were created using an automatic algorithm performed on different specimen types. MTS criteria predicts crack propagation along a path where the mode 2 is minimized, while the mode 2 influence is only visible on the initial crack propagation deflection direction, while tensile mode dominates the rest of the crack propagation process. Pure mode 2 crack propagation can be simulated accurately using the MSS criteria. Finally, on the rail track, the MSS criteria actually predicts crack propagation according to shear mode until the crack branches due to pure mode 1 with a crack deflection angle of around 70 degrees. And this concludes our presentation. Thank you very much for your attention.